This is Professor Thomas's Chapter 3 lecture video, Numerically Summarizing Data. Alright, so in the first part of this chapter, we're going to be looking at distributions of data, and we want to think about what the data looks like, the characteristics of the data. And we call these things the shape, the center, and the spread. Okay, so how we collect and organize the data will dictate the shape, the center, and the spread of the data, the variation, the center. And the center of the data could very well mean the average, or it could mean the mode, or sometimes, depending on our data, the center of the data is the median. Here are the three objectives, or actually four objectives for 3.1. How to find the arithmetic mean of a variable from raw data. Determine the median of a variable from raw data. Explain what it means for a statistic to be resistant, and determine the mode of a variable from raw data. Alright, so here we have the measure of central tendency describes the average or the typical data value. So we have the mean, the median, the mode. These are the most widely recognized measures of central tendency of a collection of a data set. The word average usually refers to the mean, but some reporters use average to refer to the median or the mode. So these three measures of central tendency can give very different results. And we're also going to realize that the average is probably going to be the better one because it's more resistant, versus the mean and median could, the median and mode could very well fluctuate or be misleading. Sometimes when we have outliers, though, the average may not be that great. It could be off, whereas the median will be more resistant to outliers and stuff like that. So we're learning this, okay? So determine the arithmetic mean of a variable from raw data. And when we say variable, we're talking about some, some data set. And also when we take the mean, we're usually taking it, we're assuming that the data is a sample, whereas the population arithmetic mean is described as mu, the Greek letter mu, and that's computed using all the individuals in the population. And mu is a parameter, whereas the arithmetic mean of a sample is a statistic. We call that x bar. Okay? So here's our definition. And this is the formal definition of a population's mean. It's the sum of all the x values, and these are the data values, divided by n, and n is the number of data values, the number of observations that we have. You can write this mathematically as the sum of all the x's, where I is the index of the x's, so they're different. And I ranges from 1 to the last number, so 1 to big N, divided by big N. The sample mean, alright, so this is like the default mean. Usually when we take the mean, it's even the calculator. You calculate the mean on the calculator. It assumes that the data is a sample from some larger population. Same thing though, okay, numerically the same. You're going to take all those values divided by n, and that will give you x bar. So here's a sample of students and their scores, and the first thing it says to do is to compute the population mean. We do need to learn how to do this using technology, so I will demonstrate how to do such right now. So if you have your TA84 calculator, you should be able to calculate the mean fairly easily. The first thing you're going to do is enter the data into the calculator. And I'm going to make sure that all of our lists are cleared. So I'm just going to clear out a bunch of lists that we might already have used. Okay. So now we're going to enter the data in the calculator, and the data goes inside of a list. So we have to go into the stat menu there and do edit, and we get to decide what list we're going to put our data in. I'm going to enter my data into L1. Now, I'm doing this because the data only has 10 values. All right, once we get past 10 and up to 20, probably not going to use the calculator just because it's too tedious. Okay, so if we're dealing with a data set with like 50 values, 50 observations, data points, it might be better to try to use some other piece of software like StatCrunch or Excel, which is fine. There's even a website that does some of it as well. Or if you don't mind using your calculator, you can as well. That's fine. So I'm just going to enter the data in, just hit 82, enter, 77, enter, 90, so on and so forth. Just enter everything in there. Alright, it looks like I have all 10 values in there, so that's good. I'm going to go second quit to get back to the home screen. And let's just make sure the data still is just stayed, right? It was saved. I choose L1, second one, and then hit enter. There's our data, so it is still there. So now what we're going to do is calculate the mean. Now there's a few ways to do this. One way is if you go back into the stat menu and go over to tests. Actually, I take that back. We go over to the second list. All right, so second stat, which is the list, the blue list, and go over to math. This is all of the different operations you can do to your list. There's many more, but these are some things that you can do. So I'll go to 3, and then I'll choose L1. Now it turns out that this way is actually kind of the long way to go about getting it. There's even a better way. There's multiple ways, but I'm going to show you the more practical way of calculating the mean once you have all your data into L1. So I just showed one way. Now the other way is to hit stat, go over to calc, and one var stat. So this is going to give you a lot of information on your data set. One var stat. So we have one variable. In our case, the variable is called score. And we're going to select it. Now it prompts you, list 1 is L1. The frequency, it's not a frequency distribution table or anything, so I can leave my frequency list blank. Or I could put 1, which basically means all the values occur exactly once. And now just hit calculate. And it gives me X bar. It gives me the sum of my list, the sum of the squares of the list. Big S, or actually SX, that is the standard deviation. It gives me, if the set was the population, the little sigma, that would be the standard deviation of the population. The N value, the number of values in the list was 10. It even gives the 5-number summary. Okay. So that's something that we're going to go over, I believe, in section 3.5, the 5-number summary. All right, I probably could even, at this point, I could probably even graph a box plot. I turn that on and choose box plot, L1, and then hit stat plot under zoom, go down actually to zoom stat, and I have a pretty box and whisker plot. If I hit trace, I can actually see what those values are. There's my median, there's my lower quartile, the 25th percentile, the minimum value out of all 10 numbers, the upper quartile, and the max. So that's the 5-number summary right there. Those values are there. So we're going to quit back to the home screen and continue on. Now, you can actually compute, obviously, the mean by hand, and this is how it would be done. Simply add them all up, divide by 10, and you're done. Sometimes you would round off to one decimal place, one more decimal place than the raw data. There were no decimals, so we'd round it off to the 10th. If there was a 10th in one of the data values, one decimal point, then we'd round to the 100th. It's just kind of the culture of what we do from stat classes to stat classes. All right. Here's another way. Let's say we decided to, it says to find a simple random sample of size n4 from a population of n10, we could use the calculator to with the seed of 14. And the C gives the calculator a starting point when it's trying to generate a list of random numbers. All right, let's move on. There it is. And our sample was a little bit greater than the mean, which is okay. It's just kind of a coincidence that the ones that appeared in our sample had values, a total amount of values, the average rate of values greater than 72. Although we did get some values less than 72 and some values greater than 72. So we had 2 below, 2 above, which is pretty good. All right, and here they're saying that it is helpful to think of the mean of a data set as the center of its gravity. The data values gravitate toward the center in a normal distribution, at least. It really also just depends on what our data set is all about. Usually in standardized tests, like our data was, we don't know if it was a standardized test, but in test exams, usually the data falls as a normal distribution. So what's up with the median? All right, so here is a way to calculate the median. Here are some steps in finding how to calculate the median. And as you can see, the 5-number summary gives you the median. We were able to calculate the median from the calculator, but it is important to know how to calculate the median by hand. It also depends on the number of values of your data. If you're dealing with an odd set of data values, then the median will be exactly in the middle. There'll be an even number to the left of the median and an even number to the right of the median. If the value is even, if all of the data values are even, then the median will be the mean of the 2 middle values once you place them all in order. All right, so keep in mind you must arrange the data in order, determine the number of observations, and then determine which one is in the middle. If it's odd, there'll be one number in the middle. If it's even, there'll be 2 numbers in the middle. And if there's 2 numbers in the middle, you'll take the average of the 2, and that will be the median. So it's possible to have a median that's not even in your data set. So it's truly in the middle. Let's move on. So here's how you would calculate the median of this. As you can see, there's 9 observations. So once we place them in order, there should be a middle number. There's going to be 4 to the left, 4 to the right. I'm looking at 217, looks good there. And 217 it is. Here's another one. There's 10 observations. The two middle numbers are 77 and 82. There we go. All right. So for the third objective, you have to be able to explain what it means for a statistic to be resistant. And so here's a data set. Notice that one of the calls is 48. Now, if we calculate the median and the mean, we have 7.25 or 7.3 for the mean, and the median is 3.5. Which one do you think would be better to describe the middle? All right, this is a dot plot showing the data that we have. So what they're saying is that the mean is not a representative of the typical calling. So the median is a better measure of central tendency for this data set. A numerical summary of data is said to be resistant if extreme values relative to the data do not affect its value substantially. It's a good point. Let's see what happens when the mean and median are very off. In other words, the mean and the median in a perfectly symmetrical distribution should be the same. But that's not practical. It rarely happens. And we have to think about what happens when the mean is pulled more in a different direction to a data set. So here's the relationship between the mean, median, and the distribution shape. Skew to the left, okay, it also means that we have a longer left tail. What this implies is that the mean is being dragged by that tail, so the mean would be less than the median. If it's perfectly symmetrical, then in theory the mean and median will be the same. And skewed to the right means now that the right tail is longer, and as such there are probably outliers to the far right. And that actually, when we calculate the mean, it pulls the mean in that direction. Keep in mind the median separates the top 50% of the data from the lower 50% of the data. So we can see that when we're dealing with the right skew, the mean is going to be greater. All right, so here we have a data set. Now, this is a gigantic data set, all right? Let's just be honest. There are 50 different values, okay? Now, we could technically enter this in our calculator. Our calculator could hold this amount pretty easily. But the expectation is you might want to get a little creative in calculating the mean and maybe even creating a chart as well. Because there's other technologies that we can use that would do that. And so using the calculator, they figured it out that we got 7.49 as the mean, and the median is 7.35. They're actually very close together. This is good. They're very close together. There is our histogram. And if I were to kind of draw in the distribution of our histogram, kind of like putting in that red line, you can see that it's normally distributed. Like that is what you would call symmetrical. The right tail kind of looked, it started to get a little longer, but for the most part, I mean, this is, if we had more data values, probably 500, it'd probably look more normal. All right. Now the mode turns out to be the number that appears the most. Sometimes there could be no modes. This happened with well, the Challenger blew up because of the O-ring failure. Simply the little rubber ring that goes on when you screw something. You got to have the O-ring, otherwise it's not going to be airtight. And you know, this was the data comes from the number of O-ring failures in all space shuttles prior to the fatal flight of the Columbia that occurred in January 20th. Yeah, it is kind of a rare thing. All right, the mode is 0, so it appears the most. Find the mode of the exam score data listed in Table 1. So there was no mode. Now there is such a thing as a bimodal. If you have 3 or more, you could be multimodal. You can calculate the mode from categorical data as well. The data does not have to be numerical. Looks like back occurred the most, and so back was the mode there. So here's our summary. Here's how you calculate the mean, the median, and the mode. Keep in mind, we do have our class notes from section 3.1 as well. Let's as you can see, it summarizes the section for you, and there are also even problems there as well. So you can actually take notes on this. Definitions, strategies in calculating the median and mean. It does have graphics and other things as well. All right. Now let's look at, next is the measures of dispersion. Okay. And we're really talking about the variability of the values, the range of the values. It's another characteristic of our data set. We have to be very familiar with our data set when we get a data set. There are 5 objectives. We have to be able to calculate the range. All right, now it turns out the range is not that resistant, so there's another measurement of the range that's more robust. That's the standard deviation. And there's also something called the variance. Then there's the empirical rule, which has to deal with more applications, and Chebyshev's inequality. Let's move on. So here's the difference between the measures of central tendency and dispersion. All right. So here, clearly we have a lot of data, and I don't want you to work with such a huge data set manually. That's not the expectation. but you should know how to handle big data. Um, and what's more practical is, data scientists will work with millions of data values, millions of rows, and the variables could be in the hundreds of thousands. There is a lot of data out there. If anyone's interested, we can, well, I'm not going to get into it just yet, but there are websites out there where you can become a part of the community to crunch larger numbers and win prizes and things of that sort. The data in Table 7 represents the IQ scores of a random sample of 100 students from 2 different universities. For each university, they'll compute the mean IQ, draw a histogram using the low or class limit of 55 for the first and the class width of 15. Comment on the results. Now, this is what we got. University A, University B. Well, what are some of the things that come to your mind? I mean, they both look pretty symmetrical. But in University A, the data is going to be more dispersed. It's going to vary more. Okay. Both universities have the same mean IQ, but University A, the data looks more spread out and more dispersed. Okay, exactly. It's pretty interesting. So here it is, determine the range of a variable from raw data. And the range is pretty simple to calculate. Again, it's the largest data value from the smallest. Obviously, outliers will greatly affect the range. All right, so really, if you want to calculate the range, it's best that you do not have any outliers. The range is 32. Determine the standard deviation of a variable. All right, so the standard deviation is based on the deviation about the mean. Now, we don't really calculate the standard deviation by hand anymore. It's too tedious. Unless you have a small data set, you probably can go for it. But the truth is, the expectation is that you use technology to calculate the standard deviation. In our calculator in the TI-84s, there are several ways to calculate the standard deviation. I demonstrated it earlier. S is the standard deviation of X. That is the standard deviation if it is a sample. If the data is a population, it's going to be slightly different. So it really depends. You need to know what type of data set you have, whether or not it's a sample or you have the full population. So this is the big formula. This is the standard deviation of a population. All right. You have mu, the mean, and you subtract all the data values from the mean, square it, make it positive, add them all up, and divide by the total number, and then you take the square root of that. There is an equivalent form of standard deviation, the computational formula, they say. And now they say here, calculate the standard deviation. This is how you would calculate it out by hand. List out all your numbers, list out the mean, subtract the mean from the data, and then square that last column, and then take the average of the last column, and then you take the square root of that last column. So we got 964, divide that by 10. So the variance is 96.4. We've calculated the variance, and it turns out that the square root of the variance is the standard deviation. It's 9.8. And the units of the standard deviation is the same units of our data value. Now, if our data is a sample, it is going to be pretty much the same formula, except you don't divide by n, you divide by n minus 1. You're giving yourself a degree of freedom. It's mathematically been proven to be a better measure of deviation when you subtract from 1. So as you can see, you have two different means. Or the mean is 79, the calculator reports when you use one of our stats. But the standard deviation of S is the mean is 10.3, and if it's a population, the standard deviation is 9.8. So in this case, if the standard deviation is 6, then from 25, if 25 is the mean, the next number will be 31. That's one standard deviation away. Pretty interesting stuff. We'll get into that a little bit more as the class goes on. This is what one of our stats would give you. They used Minitab, which we don't really use Minitab. StatCrunch could probably give this as well. We can probably look and see where that is. We can play around with that as well. All right. So whenever a statistic consistently underestimates a parameter, it is said to be biased. So here's the empirical rule. if we have a normal distribution and the mean is in the middle, within one deviation of the mean, plus or minus, will account for 68% of all of the values. All of the data values will be within one deviation of the mean. Within two deviations of the mean, 95% of the data will be within two deviations of the mean. And after three deviations, you're accounting for 99.7% of all the data values. So it's the calculation of the standard deviation is pretty important. There's a lot of different questions that could be asked based on the empirical rule. So for example, here we have the situation where it says the mean is 100 for IQ scores, right? And the standard deviation is 16.1. So we can fill out the normal distribution. Right? The IQ scores are normally distributed at bell-shaped curve. So we know between 83.9 and 116, 68% of the data will be within 83 and 116. Okay, between 116, scores between 116 and 132, about 13.5% of the values will be 13.5. Okay. So there's some more problems that they can ask as well, right? We can calculate two standard deviations below the mean, put us at 67.8. We know between 67.8 and 132, 95% of the data will exist. Pretty interesting stuff there. All right, and here's the last piece of this section. So this is for any data set, and this is just a rough estimation. It's not perfect. It's a little messy. You know, the empirical rule only works when you have a normally normally bell-shaped, perfect-looking curve. But if we got any kind of data set or distribution, whether it's skewed or not, at least 1 minus 1 over k squared times 100% of the observations will lie within k standard deviations of the mean, where k is any number greater than 1. So this holds when k is greater than 1. The model falls apart after 1. So let's assume k is 1.5 or just say 2. Right? In this case, part A, let's assume k is 3 deviations. Determine the minimum percentage of students who have IQ scores within 3 standard deviations of the mean according to the inequality. Well, let's look at it. If k is 3, then we got 1 minus 1 over 9 times 100% is 88.9%. So you could just say, hey, about 88.9% of all students have IQ scores within 3 standard deviations of the mean. The empirical rule would have said 99.7, but according to the data set we're working off of, it'd have been more like almost 89%. It's a big difference. All right, and they're doing the other scenarios there. We're now going to jump ahead. We skip section 3.3. It's just not a part of our study. We're going to look at 3.4, the measures of position and outliers. And then we'll also finish the discussion with 3.5. So here's the z-score. It's kind of a way to standardize data values. And what happens is the mean becomes 0 and the standard deviation becomes 1 when we standardize the scores. So here it says determine whether the Boston Red Sox or the LA Dodgers had relatively better run producing seasons. The Red Sox scored 876 runs and play in the American League, where the mean number of runs scored was mu equals 731.2, and the standard deviation was 72.6 runs. The Dodgers scored 804 runs and play in the National League, where the mean number of runs scored was mu equals 710.8, and the standard deviation was 60.2. Well, the first thing we're going to do is compute the z-score. So we subtract 731 from the 876, the mean, divided by standard deviation, we get 1.99. The Dodgers, we do it and calculate 1.55. So the Red Sox had run production 1.99 standard deviations above the mean, while the Dodgers had run production 1.55 deviations above the mean. Therefore, the Red Sox had a relatively better year at scoring runs than the Dodgers. What about interpreting percentiles, right? We already know the 50th percentile is the most famous one. The 50th percentile is aka called the median. Well, what about the kth percentile, denoted as p sub k, of a set of data is a value such that k% of the observations are less than or equal to the value. So if k was 80, the 80th percentile, that'd be the data value associated with the 80th percentile would be 80% greater than all the other ones out of all 100 values, 100% of the values. So this is what we're looking at. All right, P1 is the bottom 1%, P2 bottom 2%, P98 the top 98%, or you could just say the top 2%, top 1%, the largest values. All right, so Jennifer just received the results of her SAT exam. Her SAT math score was 600. Of 600 is in the 74th percentile. What does this mean? Being at the 74th percentile means that 74% of SAT mathematics scores are less than or equal to 600, and 26% of the scores are greater. So 26% of the students who took the exam scored better than Jennifer. Determine and interpret quartiles. All right, this reminds me of the 5-number summary. The 5-number summary are nothing more than a bunch of quartiles being divided up. Q2 is the median, Q1 is the 25th percentile, so on and so forth. All right, now how do you actually find quartiles though, right? You would arrange the data in ascending order. Determine the median, or the second quartile, and then you would divide the data set into halves, and the observations below M and the observations above M be the first quartile. The first quartile is the median of the bottom of the half of the data, and the third quartile is the median of the top half. It's just another way to think of it. Just really just the 75th percentile of the entire data set. So here's a data set, 18 values. Find and interpret the first, second, and third quartiles for collision coverage claims. Well, again, our calculator can compute this, but you should know how to do it by hand. First, they figured out the median, which is 735. And now we get actually it's the median of the bottom half, and the actual median is not, we didn't figure that out just yet, but here we have the upper quartile is 4668. There's our interpretation. And when you find the quartiles and the collision coverage, there it is. This looks good. It looks like StatCrunch was used this time to calculate the different quartiles. We have all 5. Basically, the min and max are, you know, considered the 100th percentile and the 0. The median is the Q2, 50th percentile. And what about the interquartile range? Well, it's simply the interquartile range is Q3 minus Q1. It will represent 50% of the data. 50%, the innermost 50th% of the data. A box and whisker plot highlights the interquartile range. The box, the range of the box, is the interquartile range. So once you have Q3 and Q1, the interquartile range is easy to find. All right, and finally, the 5th objective is outliers. When performing any type of data analysis, we should always check for extreme observations in the dataset. Extreme observations are referred to as outliers. Outliers can occur by chance because of error in the measurement of a variable during data entry or from errors in sampling. So there's actually a way to calculate outliers, and it's kind of by creating what's called a fence. the lower fence, so if you exceed the lower fence, or if you're lower than the lower fence or greater than the upper fence, you could be classified as an outlier. So you do Q1 minus 1.5 the interquartile range, and the upper fence would be Q3 plus 1.5 times the interquartile range. So here it says check the collision coverage claims data for any outliers. And what they're going to do is build the two fences. The lower fence is already in the negative. The upper fence is in the 10,000s. And we did get an observation that was 21,147 was greater than the 10,000. So that value would be considered an outlier. All right, and finally the 5-number summary. The 5-number summary consists of the smallest value, Q1, the median, Q3, and the largest. The calculator does give you the 5-number summary when you use one var stats. Drawing a box plot, well, or sometimes I call it a box and whisker plot. Basically, you just need to know the values. You need to have a number line that contains all the data values, and then you match up the dimensions of the box relative to the value of the numbers. This is a different type of box plot. All right, but this box plot actually contains outliers. You can see now that the box plot is skewed to the right. Here it's symmetrical. This one's skewed to the left. All right. What we'll do now is take a look at some problems from the homework. So we will go into assignments, and let's look at some chapter 3 assignments here. Now here we're really just going to look at calculating the mean and the sample mean. The population mean and the sample mean, they'll actually be the same. So we're going to add these numbers up and divide by 5. So that's what we would do. Add them up and divide by 5. All right, it looks actually like a nice number. If we add the tens column first, we got 20, 30, 50. And now let's add the ones. 8, 8 and 16 plus 4 more is 20. So 50 and 20 is 70 divided by 5. 5 goes into 7 once, and then we got 14. So I got 14 there. And this would be a sample, so I'm going to put it here. I'm not going to put anything here. Because X bar represents sample, whereas mu represents population. So this is the same problem. Here it says the median of the given set of numbers is 33.5. So we know the median. What is the value, the missing value? Well, it is an even number, and the median would be the average of the inner two. So 27 plus x divided by 2 is equal to 33.5. That shouldn't be too difficult to compute. We can multiply, just think backwards maybe. We could multiply 33.5 by 2. It's 67. And then just subtract that from 27. So I got 40 there. Okay. All right. This doesn't seem too bad. Some of the data values are probably creeping up there, though. This looks skewed, so the mean is being pulled to the left. I would say that the mean is less than the median. The histogram is not symmetric, though, so more like this. Okay. Let's look at this data set. How big is it? Oh, that's not too bad. All right, this data set's not too bad either. Let's take a look at 3.2. $20 questions, like 20 points. All right, they actually want us to find the variance and the standard deviation. Since it's a sample, we do s squared right here. The calculator would do this no problem. Let's do it in the calculator real quick. And I'm going to edit the data. I'll put the data in list 2. 23, 14, 3, 10, 12. Make sure I didn't make a mistake. 23, 14, 3, 10, 12. Okay, that worked. Second quit. So just remember that the data is in L2. Well, I can go into second list and go to math and do the variance. And it considers the variance to be a sample. I could do it this way. But the truth is again, you don't really want to always go to list because there's even a more practical way to go into one var stats. Problem is that one var stats is going to give us the standard deviation. Actually, I got to do one var stats of L2. So this is really important that we're using same thing with the variance 8 of L2. And the same thing with one var stats calc. You go over to one var stats and we choose L2, second L2, and go to calc. Now when you do it, we actually get the sample standard deviation 7.2. So we have to square 7.23. The way to get that value, you'd have to go into vars and actually go over to stats and choose 3. So now I actually have that value and I can square that value and I get 52.3, which is what we got at first. Okay. So we're learning how to use our calculator slowly but surely. All right. The range, the high minus the low, histograms, which one you believe has a higher deviation. We'll check how widespread it is. Look at this one. This range is 20, but this range is 40, more than 40. I'm going to go with B having a higher standard deviation because standard deviation measures how far the data values are from the mean. All right, let's click in the box. That is a lot of data values. Now, if we were to open this in Excel, will it be in one column? Well, that's nice. That's very convenient. It's all in one column. So we can do some computation in Excel if we wanted to. We choose data. We choose, actually, let's go to formulas, insert a function. Let's check the, well, what did they actually ask for? They wanted the problem was to calculate the standard deviation, the sample standard deviation. So we go down to standard deviation is what we want. And we want it to go from, hold on there. We can go equals STDEV, and we're going to go from A1, let's see, let's make sure we can get that right value in there. A1 all the way down to looks like I changed the first value of my data set. That's not what I want. Let's go back. All right. Whoa. Okay. So it's originally it was 0.87. Now the question is how do you actually calculate standard deviation using Excel? And what I'm going to do is go in here into my function, and I'm going to say equals. I can put it here. Equals STDEV. I'm going to use, this represents it's from a sample, so let's use a P, and we're going to choose numbers A1 through 48. Close it off. And I got it. Okay. Now, the data value is in the hundreds, so I should round my standard deviation to the nearest thousandth. So I'm going to put 0.036, and I'm pretty sure they asked us to round to 3 places as well. 0.036. Let's check it. It said good job. Now we got to answer a question about it. Now, what if we actually wanted to do this in StatCrunch? Well, let's get another problem. I'm sure there's another one that's similar to this one. Let's open it. That's a lot. Well, it's 2 different kind though. That's different from what we were just looking at. Well, we should still let's see. Yeah. Well, if I did open it in StatCrunch, let's take a peek. My variable would be pause, and I would go over to stats. Stats is where all the good stuff is. Summary stats is really good. But that doesn't give us what us want. Let's go to calc. Let's go over to data. That's where you want to manipulate your data. We can do all kinds of stuff. So if I choose pause and I want all of this stuff, I got it. Hit compute. let's see here. They're saying I did not select any of these. Oh, we had them all selected, didn't we? You must select at least one value for select column. Oh, okay. This guy was, oh, it wasn't selected there. So now we're good. Let's cancel. Let's just go back in there. We went into stat. I believe we went into table. Let's see. Hold on. Column. Choose pause. Everything's selected and hit compute. And now look at what we have here. We have the standard deviation, and let's see if that's gonna like that if we're able to use that. Also, they're assuming that it's a population. You see, population, not sample. That's that's a very important distinction. I'm not even sure that they'll accept 6.83 or 6.8 because I think I set it as a yeah, I set it as a sample, so we need to go back in. We need to make sure that StatCrunch knows that we're dealing with a population, not just a sample. So what we'll do is go back in the stat and go back into summary, columns, and it doesn't even, it seems to me that, well, once I select pause, do I get the option of letting it know that I'm dealing with a population here? All right, hold on. Let's go back to stat. Yeah, let's go into summary stats. Yeah, this, I think they're not making it obvious that if we're dealing with the full population. Um, so that could be a potential problem there. I think it just doesn't believe that we're dealing with a population. All right. Well, we could probably just continue to use Excel maybe for something like this. It's pretty small still. We go in here. It's really puzzling though. Huh. We see what the problem is. So we go to row, column. It does a lot for us that we want. This is all good stuff. Select there. That's good. Build. No. Okay. Hold on. Let's cancel that. What about standard deviation? Standard error? No. Group by. Good. Yeah, this is puzzling. Let's choose all of that stuff. Other statistic. Could be. Let's go back to stat. They should give us the option to calculate the deviation of a population. So just don't see it. Let's go to standard. STD. Nah. I'm gonna add that function. I think STD is the guy. That's probably the one. Well, it looks like my column didn't get moved over. It should be pulse, right? I should have pulse in there. Let's go back. What if we were to just type it in? Six point 6.8. Oh, they're giving me the same exact value. And they wanted it to one place. Hmm. Yeah, no, 6.8 is no good, huh? All right, well, we'll have to do some research on that. That's surprisingly, StatCrunch did not like that. Let's look at some more problems from this section. A few more. It all looks pretty straightforward. Let's go to 3.4. All right, let's take a peek at 3.5. You can see it's right skewed. 25% of the data is in this range from 0 to 60. 25% of the data. It's the 5-number summary. We could open this up in StatCrunch. No problem. We could calculate the 5-number summary. And we have it now. We have the median, mean, max, Q1, Q3. That's the 5-number summary. Put that in there. It should give you full credit. All right, we're going to end the video here. Hopefully this was helpful. And if you discover a way fast before I do on calculating the standard deviation of a population using StatCrunch, mention it so we can investigate it and try it out on our own. Until next time.